practice problems regarding the camera, both the view matrix and the projection matrix. Let's start just with building these matrices. So first problem here, build the view matrix for the position and orientation of a camera. That is as follows. And then we have this eye, we have the center, which is the point that it looks at, and we have the up vector. So the idea here is that we have this position of the camera. We're imagining that the camera is like an eye looking this direction. So this is the point I. This here is the point center that the camera is looking at, and we imagine the camera is looking this direction. Then this up vector is just a general purpose up vector for the system. And the idea is that we take these 2 points, and we can actually erase this vector here and say we're going to take the difference between these points, center and I, except we're going to do I minus center, so it's going to be a vector turning this direction, which is going to be kind of the z-axis of the camera's coordinate frame, or the n vector. Then we're going to do a cross product between n and the up vector and get a vector that we imagine sticks right out the right side of the eye. And finally we do a cross product between n and that vector u and get the vector v, which is the actual straight up vector here. So what we end up with is an imagined camera here with a coordinate frame being n and u somehow straight to the right and v straight up. So what we're going to do is we're going to say n equals I minus center. Then we're going to do u equals up cross n, and finally v equals n cross u, and this will build our coordinate frame. When we've done this, we're going to set up the view matrix, which is ux, uy, uz, and finally the last component is minus I dot u, and then the same for v and n, vx, vy, vz, and minus I dot b, nx, ny, and z, and minus I dot n, and then last line 0, 0, 0, 1. And this is the matrix that we're going to build. But rather than actually writing this up out here, I just set up an Excel spreadsheet here. So let's take those numbers. Well, I've built part of it, but we're going to build part of it as we go. So the numbers are 3 minus 2, 8 for I, 3 minus 2, 8 for I. We have 3, 1, 3 for center, 3, 1, 3 for center, and we have 0, 1, 0 for up. So okay, what we did earlier was we said n should equal the cross product, no, n should equal I minus center. So the x is this minus this, the y equals minus center. Here we have I minus center. So this is our unnormalized n vector, and we have to make sure that we have to take these vectors here and we have to normalize them before we put them into the matrix itself. So here we have the n vector. Next we have u equals up cross n. So the x coordinate of u will be, so this is up cross n. Up cross n. So this is going to be, so the x coordinate will be the y coordinate of up times the z coordinate of n minus the z coordinate of up times the y coordinate of n, like so. And here we have, so it's up cross n minus times this, and finally we have this times this minus this times this. Okay, so that's 12 times 15 minus and minus, okay. So that's u, and finally we can take the cross product. Well, what we can do now in program is either we can normalize these two first and then take the cross product between them, giving us a unit vector again, so we only have to normalize two of them. But here it's okay to let's just take the cross product. So v equals n cross u. So for the x coordinates we'll have equals this times this minus this times this. Here equals n cross u, this times this. Finally, cross u minus times this. So that would be our v vector, the actual up vector, having the same coordinates here. Looks like it's looking 45 degrees. You can inspect that and kind of check out the numbers if we want to make sure. So let's take the length of each one of them. It would be the square root of this to the power of 2. Let's just do this times this plus this times this plus, okay, great. That would be y13 times y13, so we have the square root of that, like so. So that's the length here. If these lengths are working properly, let's see. Yes, okay. So these are the lengths, and finally I can go here and I can say this equals the x coordinate divided by the length equals the y coordinate divided by the length. This equals the z coordinate divided by the length. Right. And we can take this, send it down like that. So now we should have the normalized vectors here. So now what we have to do is we simply have to build this matrix here. So we have this matrix here, ux, uy, uz, and then this dot product. So let's just start with ux, this equals y equals 0. So, and finally here we have this equals, so basically say minus, then we can take the entire thing like so, and say this times this plus this times this plus z times z. So, and well, doesn't matter, let's just do the same for the others. Equals minus this there equals minus parenthesis this times this plus this times this plus this times this equals, just to look that these are all okay. So here we have minus I dot u minus I dot v minus I dot n. We have to make sure we do this with the normalized vectors and not the original vectors. So the vectors should all be normalized before we fill in the matrix. So now we have the matrix. So that would be the answer to the first question. These are the actual numbers, but the method is basically here, just filling in this matrix. So, second question here, build a projection matrix for the following camera perspective. So we have a field of view of 62 degrees, we have an aspect ratio of this, near plane 3 and far plane 103. So the idea here is basically that we're going to build data that will in the end be data for top equals something, bottom near and far. Oh, sorry. Let's start with right, left, and near and far are actually given. So we're going to fill them in into the matrix. So from the field of view angle and the aspect ratio, you can say top is going to be near, which is n, times the tangent of the field of view angle halved. And just make sure that if you're using a tangent that takes in radians, that you have to change field of view from degrees to radians. But the idea is this. Then you can put into this times pi divided by 180. Bottom simply equals minus top, this type of perspective. Right equals top times the ratio. The ratio is simply the aspect ratio of the screen that we're going to be projecting this onto. And finally left equals minus right. And then finally, what we want to do is fill in a matrix. So the matrix we have here in the end is the projection matrix, and so what it finally looks like is we have 2 times n divided by right. Let's just make that r for right. Right minus left. We have 0 here, 0 here, and here we have 2n divided by top minus bottom. Here we have 0, 0, then we have minus f plus n divided by f minus n. Here we have minus 2 times f times n divided by f minus n, and the bottom row 0, 0, and we have a minus 1 here and then 0. Here we have 0 and 0, and in this aspect ratio we're going to end up with 0 here and here as well. But the correct thing for the frustum would be right plus left divided by right minus left, and we have top plus bottom divided by top minus bottom. But seeing as right equals minus left, or left equals minus right, we're going to get 0 in both of these. But this is the entire matrix that we're going to fill in. So we can just calculate each of these. Since we've already calculated top, bottom, left, and right, you can calculate each of these and just fill in the matrix. But again, we're going to look at this in Excel here. So we had a field of view of 62 degrees. We had a ratio of 4:3. We had near 3 and far 103. Let's see how this is going to look. So now we fill in the matrix and we say this is going to be 2 times n divided by, wait, I don't have everything we need yet to fill in the matrix, sorry. Start by calculating top here. So top equals near times the tangent of field of view divided by 2 field of view divided by 2 times pi, so good enough approximation, divided by 120 degrees. That's all inside the tangent. So that ought to do it. So this is top. Bottom equals minus top. Right equals top times ratio, and left equals minus right, like so. Okay, fine. So now I have what we need. So here we're going to say this equals 2 times n divided by right minus left. This equals 2 times n divided by top minus bottom, like so. This equals minus 2 far plus near divided by far minus near. This equals minus 2 times far times near divided by far minus near. Okay, fine. And finally we have 0, 0, minus 1, 0. And okay, so now we have, and these will end up being 0. We can put in the formula for them if we want. This equals right plus left divided by right minus left. Here like so. And this equals top plus bottom divided by top minus bottom. Now I can change these numbers around here and get a proper frustum matrix, even though we get zeros for these particular numbers. And so we have the matrix. These would be the numbers in the projection matrix for that camera. So finally we have 3 here. Given this setup from 1 and 2, what are the clip coordinates for the vertex with global coordinates for 2, minus 1? So imagine that the global coordinates come from already having multiplied this with the model matrix, or maybe we just imagine that the model matrix is unchanged, so we're just putting our coordinates straight into global coordinates, so we have the same coordinates as the camera is set in and the lights are set in. But what we want to do now is we want to say these are the coordinates in our global 3-dimensional world. We want to get the clip coordinates for them, and the clip coordinates are basically the 2D coordinates within the clipping window, not within the viewport itself, where we end up transforming the clipping window onto the viewport later on after we clip. But these are the 2-dimensional coordinates in the clipping window, and then the pseudo depth. But the pseudo depth kind of scaled to ranging from -1 to 1 before we actually stretch them out onto whatever bit depth we have in the depth buffer in the end. So the way to go from global coordinates to clip coordinates is simply to multiply with both of those matrices. So 4, 2, minus 1. Let's go here and say we have 4, 2, minus 1. So we take the view matrix, multiply that with the global coordinates, and we get the I coordinates. I say this equals this, this equals this. So we're simply moving our current I coordinates down here, and we say we now multiply the I coordinates with the projection matrix, and we get this. But as you can see, the last coordinates here aren't 1, so this isn't a proper point. We want something that is ranging from -1 to 1 in all dimensions if it's within the clipping volume. If it's not within that range, it's simply outside of the clipping volume and it will be clipped. It's not illegal, but it's something that won't show up on the screen. We set this vertex up so that it should be in front of the camera. So it doesn't make sense that the numbers are so high. That's because we still have this number here. So we need to do the prospective division, basically saying we're going to set up a final point here where the coordinates for the point are basically this point here, but shortened by the 4th coordinate, the W coordinate, the homogeneous fourth coordinate. We'll divide it by this. Here we have this divided by 9775. And finally we have Z coordinates divided by this. And we've seen this before because these coordinates are simply the negative P coordinates. So no, negative Z coordinates of the point here. So if this is the point P, then these coordinates all have a common denominator, which is the negative Z coordinates of this point here. And then we have whatever else in the numerator. But finally we also have this divided by this, which obviously becomes 1. So now we have our point. So these are the clip coordinates. These aren't the clip coordinates because we haven't divided the fourth coordinate into all of them. But these are the coordinates, and they do range somewhere between -1 and 1, meaning that this is a vertex that will be within the clipping volume and thus won't be clipped away and is something that will show up on the screen once rasterized. So that's it for these few problems here on the viewing matrices and projections. So the camera projections, the linear algebra behind the camera of OpenGL.